Welcome back to Geology. Today I want to start with earthquakes, chapter 8 in your text. And it starts off with a nice photo showing a strike-slip fault. And so remember, strike is going to be a compass direction. Think of it like a bearing, but the bearing is always in reference to north. For example, in this picture, if north is at the top of the picture, then west is on the left here, east is on the right, south is at the bottom. So this fault has a strike direction. It's slipping in that strike direction. It's moving in that strike direction. So you would say this strike is trending north, but it's some degrees off toward the east because it's off toward the right. So it would be like north. If I had a protractor and measure this, I'd measure like 40 degrees. So I'd say it's north 40 degrees east. That would be the strike of this line, or the bearing in this direction is northeast, north 40 degrees east. So that's one of the things we'll talk about when we do faults here. But before we get going here, remember the key thing about earthquakes is that it's going to be the release of strain energy. So rocks, tectonic forces are moving, causing plates to move, and they're grinding past each other, and the rocks are accumulating strain. So remember, strain is a deformation. It's a bending, and there's a variety of strains. But in this case, the strain we're concerned with is an elastic strain, elasticity. So here this stick is being bent, and it's accumulating strain. It's bending, it's elastic. But here we've actually snapped it, so that's an example of a brittle strain. But I want you to look at the edges of the stick here. So because there was energy that was accumulating in the stick here, in the molecular bonds of this stick, when that stick snapped, it vibrates to release that strain energy. And in the end, the stick is back to its normal self. It's back to being straight. So one thing about elastic strain, which is the one that causes earthquakes, is that the material bounces back to original shape. The stick is straight again. So that's an example of elastic strain, release of strain energy. What causes earthquakes? Most by slip on a pre-existing fault. That's one of the things your text makes note of. There's a pre-existing fault and there's going to be movement. And usually we call that a stick slip, a stick slip. So that means that there's a snag, some area of the fault is locked, and as the tectonic forces are moving, that locked area keeps accumulating more and more strain, and eventually it slips, only later on to be stuck at another position for a while, accumulate strain, then it slips again. So it's kind of like how the caterpillar moves. It moves its front, and then it moves its back end and front. So that's what we mean by stick slip. Sometimes we call that a long-term slip rate. But other factors that can occur is you can have a sudden formation of a new fault where there's these microfractures that could develop. Sort of in this picture here, we get these macrofractures developing, and eventually the microfractures connect and they slip, forming a brand new fault. And that's one way. It's not as common because most of the quakes will occur on an already pre-existing fault here. You could also get a sudden change in atomic arrangement in minerals, and that is called a phase change. Usually it's dealing with density, and that occurs in the mantle under higher pressures, deeper regions in the mantle where rocks are still behaving brittly or solid. They can shift to these more dense varieties. Large landslides can cause earthquakes, meteorite impacts, nuclear bombs. In fact, there's seismologists are employed by the government making sure that the nuclear treaties are upheld. And then movement of magma under a volcano and volcanic eruptions can all lead to earthquakes. Obviously earthquakes cause destruction, ground shaking, buildings toppling, liquefaction. We'll talk about that in a little bit. Tsunamis, and here's the 2011 Japan earthquake that we'll say more about in a little bit. And then now the next part here deals with faults, and there are going to be two general types of faults. One is called a dip-slip fault, and the other one's a strike-slip. First, let's look at the dip slip. So a dip is an angle measured from the horizontal down to the geologic surface, right? So the dip would be the angle from the horizontal down to the fault line here. That's the dip angle right there. Faults are going to be these fractures in rocks where slip occurs, right? Because there's slippage, and slip is a displacement along that fault. The way we name faults is really comes from miners, and miners were interested in ore deposits, mineralization, and because a fraction of rock allows fluids, especially hot fluids that might have minerals in them, to move through here, miners would dig these mine shafts into the fault fractures, and the block above the fault plane. So this is a fault plane right here. The block above that fault plane is called the hanging wall block. You can hang a lantern from that block, bump your head on that block, right? Now, the footwall block you could stand on. So the footwall block is always beneath the fault plane, right? So depending on which way the hanging wall block moves, we will have a name for that fault. So let's look at the first one, the normal fault. This is a dip slip fault, and here the hanging wall block moves down relative to footwall. Hanging wall block moves down. So that's usually occurring with tensional stresses, right? See the two arrows pulling away here? Tensional stresses. For the reverse fault, this is opposite, where we're going to have the hanging wall moves up relative to the footwall. So the hanging wall is moving up, so we're seeing squeezing or compression, right? So again, footwall always underneath the fault plane, hanging wall always above or vertically above the fault plane. So dip slips, moving in that dip direction. Now the other special type of dip slip fault is called the reverse fault, or sorry, the thrust fault. And the thrust fault is a special type of reverse fault. Again, you see compression here, but it's a low angle reverse fault, less than about 45 degrees. Here they have 30 degrees, and you can see the hanging wall block is moving up relative to the footwall, and you'll see this displacement of a thrust fault. Now for strike slip faults, they're moving in that strike direction, that compass direction, as I showed earlier. So a compass direction, a reference to north, and so they're slipping in that strike direction, slipping in that direction. And so usually these faults are nearly vertical, tend to be vertical, and slip is in that strike direction. Kind of looking at displacement, this is from the 1906 earthquake up near the town of Olima, north of San Francisco Bay, showing a displacement that occurred during this earthquake, right? There's a displacement, and the trace of the San Andreas Fault goes right through here. Some displacement occurring. You can see this road here is offset. This is, I think this is a Hecker Mine earthquake that occurred in the late 1990s down in the Mojave Desert region. So here's tectonic stress working on this rock here. Here's the fault plane right in here. The rock begins to accumulate strain. And that's like pulling back on a bow and arrow. So if you have a bow and the farther you pull back on the bow, when you release the arrow is going to go farther if you pull it back, or if you accumulate more strain, the more you bend the bow. So in this example here, I see tectonic stress forcing this part of the rock to the right, whereas this stress is forcing it to the left. We accumulate that strain, and eventually the rock just will rupture. It can't hold on anymore, and it'll slip. In fact, the slip on the fault will result in release of that strain energy. So here the strain energy is being released after this rupture, and then as a result, the rock is back to its square shape, and then the strain has been reduced or relieved here. And so now, as these forces continue over time, the strain will accumulate, and then it'll be bent again, and then the same process will occur again. Now, one of the questions I have is where does the elastic strain accumulate? And where it accumulates in the minerals and in the rocks along the tectonic fault plane there. And so think about the molecular bonds between atoms in minerals as being elastic. They can bend, they can twist, they can torque, you can pull it apart, you can twist it. And so these chemical bonds are elastic. And so as the forces, the tectonic forces and stresses are affecting the rocks here, these bend, and they'll bend and bend until there's slip on the fault, and then that energy is released. After the 1906 earthquake of San Francisco, H.F. Reed tried to interpret what was going on, tried to decipher what happened to release that energy. And he determined that first, well, in fact, he determined this elastic rebound theory. And there's three steps. Rocks are strained first, then you get that rupture to occur. And really the rupture is the slip on fault. Once that rupture occurs, that energy that was accumulated in the minerals, in the rocks, is released. And it's released in the form of earthquake waves, seismic waves. So remember, seismic means earthquake. Types of seismic waves. There's, and we talked about these when we did plate tectonics, so you can review your notes there. But the P waves move by compression and dilation. And the S waves move by a shear force, sort of like if you're wiggling a rope. Remember, the body waves travel within the earth, right? So my little cartoon down here, these are body waves. Now, the other group of waves are called surface waves. And those two, one is called the love wave, the other one's the Rayleigh wave. And I'll show you how those move in a moment. But those will not form until the body waves that form down here, the P and S waves, reach the surface. And so, in fact, the love wave is more of a side-to-side shaking, whereas the Rayleigh wave are more the undulation, the waves you might feel like. In fact, during an earthquake, the Rayleigh wave will make you feel like you're on a boat, kind of those undulations. Another question I have is on fault planes. Some fault planes dip at a steep angle here, maybe like 70 degrees here. Other fault planes are vertical. And so some important features to note here. Here's the surface. I got some trees in the house here. And the surface break that the fault plane makes with the surface is called a fault scarp. There's fault scarp. And the focus of an earthquake is where rupture occurs. The focus will always occur at depth. And then the point directly above that focus is what we call the epicenter. So in this example, the epicenter does not coincide with the surface trace of the fault. So with faults that are dipping not at 90 degrees, something less than 90 degrees, you'll find that the epicenter will not coincide with the fault. The only time you'll get an epicenter to coincide with the surface trace of the fault, in this case it's right at the fault scarp, is if you have a vertical fault. In this case, the focus is down here, and then you see right above it the epicenter on Earth's surface. Now, other things I've drawn here, when rupture happens or when there's slip on the fault at the focus, you'll see the waves, seismic waves, leaving that point in all directions. Some go through the mantle, and some go up towards the surface here. And so these wave fronts, geologists, you can draw these, and so you might get tired of drawing all these. So what you could do, you could show these vectors. And the key thing about vectors, they show the direction and the relative strength of the waves. So just know that along the vectors, there's really wave fronts that are going to be perpendicular to them. How do we determine active faults? One that's ruptured in Holocene time. Holocene time is the past 11,700 years ago. We haven't really been in California that long. I mean, the gold rush really populated the state. We started keeping more records by the 1850s. So to determine if a fault is active, well, geologists have to use something called a fault scarp, right? And so the fault scarp is a surface break, right? It's a surface break, and that surface break will break young Holocene sediment. Usually that's loose material. So if the young rock is offset by the fault, then it's a recent faulting. So in fact, I say here, the presence of a fault scarp indicates Holocene faulting. And that's important because after the 1971 San Fernando earthquake, which was a magnitude 6.6 and caused incredible amount of damage in Southern California with freeway systems and hospital buildings and schools that were built near these fault zones, this law was passed, or an act was passed. It's called the Alquist-Priolo Zoning Act of 1972. And it states that you cannot build within 50 feet of an active fault. And if your building was made prior to 1972, then there's no permits for remodeling, not even a remodel. And if you try to sell your property, you're required to disclose that you're within an active fault zone. So that's why it's important to understand where these fault scarps are, and geologists look for these when new building sites are being proposed.